Hi, I'm Conlon Foster, and this is ENME351 Lab 6 Digital to Analog Conversion in Servo Motors. Here we can see the servo potentiometer circuit, where the input of the servo is set to the digital pulse width modulation pin 9. Rotating the potentiometer will rotate the servo accordingly. Attached here is the Arduino code, which allows our potentiometer to control the servo motor. Our T control value ranges from 1000 to 2000 microseconds, and this goes in accordance with the rotating angle of 0 to 180 degrees. By finding a duty cycle where both extrema are left out, the servo motor will appropriately rotate. It is then delayed for T period, or 20,000 microseconds. The servo used is an SG92R. The rotation of the servo motor by the potentiometer is shown here. It has the full range of 180 degrees, and additionally, the duty cycle range is shown on the serial monitor. Here's my DAC conversion table, where the Arduino full-scale voltage range is 5 volts and the system is 3 bits. Here we see the 3-bit DAC I created using switches in Circuit Lab. To verify that the system works, I created a time function in which certain switches are closed. Here we can see a 001 code and a 101 code accurately being reflected in the circuit. You can verify this using the table I had attached previously. The monstrosity here is a 3-bit R2R DAC. It's a model of what I had constructed in Circuit Lab. The brown cables here are currently connected to ground. They represent the switches. We have 3 of them, making this a 3-bit DAC. When all 3 of these are connected to ground at the beginning, this represents a 000 code, which displays a serial monitor, 0 analog bits, and an output voltage of 0 volts. To make this code 100, we would turn the far right switch on by connecting it to the yellow wire, putting it in accordance with the top section. The serial monitor now displays 513 analog bits and 2.5 volts for a decimal code of 4, binary code of 100. If we connect the brown cable on the far left to turn the switch on, the code is now 101, or decimal code of 5. Our output voltage is now 3.13 volts, which is a rounding of 3.125 volts. If we turn the final switch on, our code is now 111, or 7 in decimal, which will display our maximum output voltage of 4.38 volts, which is a rounding of 4.375 volts. In order to do this in Arduino, I converted the least significant bit voltage into my analog bit units, and then solved a traditional DAC conversion equation. Next, it was time to add the servo into this DAC circuit by making an analog write command based off the duty cycle, which in itself was based off of our output voltage. With a very simple amendment to the circuit, I have added in a servo motor to be driven by our voltage output. With an addition to the code, I have mapped the duty cycle from the voltage output, and this is analog written to the pulse width modulation 9th digital pin, which controls the servo motor. So, when I move our pins from off to on, put it in the wrong. So using the DAC, our servo motor can be oriented in 8 different positions as a result of the 3-bit DAC, 2 to the third, or 8 total different outcomes. This compares to the potentiometer in exercise 1, which had 255 different outcomes based on our duty cycle. Well, really, since my duty cycle was limited, it only really had 184 outcomes, or about 180 degrees, 1 degree for every 2 degrees turned on the potentiometer. In order to make our step size smaller, we would simply add more bits to the DAC circuit. In order to do that, we would add more switches, and more switches, and more switches. And with each increment, the step size in our servo motor would continue to get smaller. Thank you, and have a nice day.